that it looked wrong. That's how touchy it is.
Sounds like a project not for anyone to take.
All right, well, let's go ahead and get rolling. So tonight we've got one of our own, Mr. Parker Lessing's going to be talking to us about astrophotography, how he does astrophotography, some of the tools and software that he uses. Anybody's seen any of the images we've shared with everybody on the Facebook page, he's taken some awesome images, of which a few of these are right up here on the screen right now. So I will turn it over to Parker and let him take us through it.
Okay, thanks. Well, I need to preface any comments that I have to say that I am on the early part of the learning curve of this journey. I'd always been interested in astrophotography, but really didn't do much with it until about 2 or 3 years ago. And I found that, I would get software, free software incidentally, because I really enjoy free. I would look at YouTube stuff on how people were using it and read about how people were using it, and I thought, well, this is pretty straightforward. And I'd go out and apply what they're doing on the software, and I would get some stuff, and coming from nothing, I was kind of happy with what I was seeing. But it didn't take long before I really started raising questions. Well, why are they doing it this way? One example of that question is when it comes to stacking images. Without thinking about it, I thought, well, when you stack, don't you want to do a cumulative stack so that you're bringing in more light? And so I would try that, and I'd look at the image, and it looked like I was taking something in the daytime. Everything is washed out. None of the bright highlights were there. You pick up some of the fine detail, and so I thought, well, what do they say I ought to do? And they say, well, you ought to do some average stacking. And I got thinking about that. Well, if you're doing average stacking, after the average, the photon count that you're actually dealing with there is really no more than what you have on a single frame. So how is it that this works? And so that leads into some comment discussion about signal to noise ratio. And okay, what's really behind the signal to noise ratio? Why does that work? And so that really led me into trying to step back and try to understand what are some of the fundamentals here, which I'm going to go over. And I know in advance that many of you are way ahead of me on that, but this is part of the journey that I went through. And as I started understanding the fundamentals, most of which I already knew, but I had not really thought about it in terms of astrophotography or imaging. And once I started making the connection on that, the things that I was doing, or the smart guy said you ought to do when you use this software, started making sense. So that's kind of where I am right now. These images, all of these images that you see here, with the exception of the sun, were taken with a color ZWO camera. And I'm going to talk about sensors and photosites here in a minute, not talk long about it, but just briefly. And when I bought my solar telescope this summer, folks were saying, well, you really ought to take images of that using a monocolor camera. So I thought, well, I got the money invested in the telescope, I might as well get a monocolor camera. And why do I want a monocolor camera? Well, they say you're going to get more detail, so then I start thinking, well, why am I going to get more detail on that? And the answer is that this monocolor sensor right in here has 6.4 million photosites. So that says I'm capturing 6.4 million pixels in my image, which is a lot of detail. In my color camera, it also has roughly 6.4 million photosites. But since it is capturing in color, in effect, my image is only dealing with a third of those, because some of those will go to green, some of those will go to the blue in the barometric, some will go to the red. And so now I'm thinking, well, if with this, and I'm not terribly satisfied with the detail on these, if I can increase 3 times the detail or number of pixels in effect on the image, I ought to be able to pull out a lot more detail. In fact, I look at the stuff that Dave does, his planetary stuff, and I'm just blown away with the detail on that. My guess is that he is using in addition to the fact that he's got very good technique, that he's probably using a monocolor camera with a bare wheel to introduce the colors on it. And I want to talk to him about that. But anyway, I want to kind of take you through some of the fundamentals that I put together, and then how they impact image quality in taking images. And then at the end of that, I want to show you a list of the software I use, and then very quickly actually run through some of that software so you can see the application of some of the things that we'll talk about, like stretching and curves and wavelets, which is kind of a mystery, and a few other items. These are my telescopes. This is a 4.5-inch Astrotech. Astrotech is known by many names, depending on the retailer that sells it. A lot of places will sell it with the name of Stellar View. Orion sells it under a name. I think there's about a half dozen names that it's sold under. It's a 4.5-inch diameter aperture, an f7 scope. So it's a nice scope. And the thing I like about it is that when I break it down, each section is at the most maybe 15 pounds, and so I can manage it. I can carry that around. The scope on top is a guide scope that you can use for polar alignment, and to be quite honest, the main thing I use it for is to put it on when people are looking at it, because it just looks cool. It just looks cool up there. The first scope I had is this 8-inch Schmidt-Cassegrain. It's a Meade, focal length 2000. It's an f10, and here it's set up to do some planetary imaging. I have my camera attached where the eyepiece goes and running into my computer. This is the telescope I bought this summer. This is a Lunt solar telescope. It's a 60 millimeter. The focal length is 420, so it's also an f7. And the thing that's interesting about this, it's got a little tuning device here that it's pressure tuning. And the pressure on it is set right between what you would want for optimal surface detail versus what you would want for prominence. I was losing the word there. And I kind of like it that way because I can easily get both. And I can change the wavelength tuning just a little bit, and I can nicely pick up both. And if I can't see both, then when I get to my imaging, they're both there. This is just this scope with my digital camera set on it, which I use for wide view imaging, such as going after things like the North American Nebula or the Andromeda Nebula. They're just too wide a field of view to get into a tiny little camera like this. So where I started my journey was, how do I go from this to this? And the thing that really strikes me as an interesting part of this question is that this and this are the same capture. And so what I had to do and had to learn how to do is how do we pull the detail out of an image like this so that we can reveal the whirlpool galaxy. And a lot of what I'm going to talk about is how we do get from A to B. So, some of the things I'm going to go into, I'm going to briefly touch on some of the background fundamentals, sensors, photosites, bit depth, dynamic range, exposure time, F-value, gain, photosite well capacity, and I'm not going to spend much time on that. That's going to go real fast. And then, how do we control noise? And you know, that's a big part of imaging. And I hope you'll forgive me to talk about how to control shot noise. I have to step aside for a moment and introduce some statistics. A lot of my background is in statistics, and that's one of the things that I taught a lot. And so, you know, I just couldn't resist the temptation. But quite frankly, when you talk about noise, signal-to-noise ratio, and why does that improve the signal, it's, in my mind, inescapable. You have to talk about the Poisson distribution. So we will do that. And then introduce dark frames and flat frames, and post-processing, histogram stretching curves, and then finally look at some software application. All of this, it seems to me, you can break down into two sets of activities. One activity is capturing the image itself, where we are trying to put in the computer the impressions of the photons that we are capturing. And the second part is processing that image. And I could be wrong on this, but it seems to me that they're separate activities really requiring different skill sets. When we get to processing, you know, in capturing, I want to capture as accurately as I can. When we get to processing, it seems to me that that's really, a lot of that is personal taste. Because what we're doing is that we're creating images not for scientific purposes, we're creating images to look at and to enjoy. And taste comes in on that. For example, if I am trying to, you know, go back to this previous picture, if I'm trying to bring this out of this, where do I stop? I can really darken the background and see more fine detail, but in the process, the sky looks artificial. You know, the sky is not black, the sky is kind of gray. And what is your taste and preference on that? So it seems to me that the processing is, you know, a lot of that's kind of an artistic taste to it, our personal preference. Okay, let's quickly review. Sensors, as we talked about and you all know, are silicon photosites that arrange in a matrix, and each cell of that matrix corresponds to a pixel in the final image. And, you know, we talk about photons, you know, being light. And, you know, what are photons? Photons are, and this is kind of a tongue twister for me, discrete subatomic particles of electromagnetic energy that we call light. And, you know, when I talk to some folks about light, you know, they say, yeah, what do you mean it's a discrete particle? You know, I look out there and it's continuous. And they have the notion that light comes in a never-ending or breaking wavelength. But, you know, that's not the case. When we look at the fusion that takes place in the core of the sun, where we're fusing hydrogen into helium, you know, energy is released, and some of that energy is in the form of packets, one of those being photons, which when they come to us and they strike something, it forms what we call light. You know, and of course, you know, it takes the photons maybe 200,000 years or longer to work their way through the sun, and they get to the surface, and then bing, 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 these things are being shot out all over the place, and they come to us, but at a level of frequency that it looks continuous. But if we were to take a beam of light and to slow it down, 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 until we're really dealing at the subatomic level. We wouldn't see a beam of light. What we'd see is a bunch of light spots going on and off, on and off, on and off, on and off. So, and why do I mention this? Because knowing that photons are discrete particles tells us that we can use a particular distribution of these photons called the Poisson distribution. Knowing the Poisson distribution helps us understand signal-to-noise ratio. So, very quickly, what happens when a photon strikes a sensor? Well, it produces a charge that's held in what we call the photocyte's well. And this charge is expressed as a digital value that's proportional to the number of photons that struck the photocyte. So the more photons strike in the photocyte, or more light strike in the photocyte, the greater this digital value. And then the camera's what we call bit depth determines the maximum number of these digital values that can be stored. So if our camera or processor is an 8-bit, this means that there's 256 different levels that can be stored. If it's a 16-bit, 2 to the 16th power, then there are 65 million plus levels that can be stored. So why is this important? Well, let's say that we are capturing an image of an extremely dim, faint nebula. And let's just, for purposes of illustration, say that this image and the digital values are stored in the dimmest 20 levels of an 8-bit exposure. Those same 20, that same level of light, if we're looking at a 16-bit processor, would be stored in 5,120 different levels. So obviously, going from 8 bits to 16 bits means that we have a lot more information. A lot more information, which means in our imaging, we're going to have an awful lot more detail. Okay, dynamic range. Dynamic range is the ratio of the brightness to the dimmest signal. We can talk about the dynamic range of the signal that we're looking at. We can also talk about the available dynamic range of the sensor. The dynamic range of the sensor determines how much of the target's dynamic range we will capture. And there are a number of things that will impact the dynamic range that we're working with, the dynamic range of the sensor. For example, time exposure. Long exposures obviously are going to capture finer detail, but they have the potential to oversaturate or overexpose bright highlights. And so we're losing information. On the other hand, a short exposure will capture the bright highlights at the expense of the dim detail. A telescope or camera's f value can also greatly impact dynamic range, and there's a big relationship between the f value and exposure time. If we look at a digital camera, like a digital single lens reflex camera, it has a diaphragm in there, kind of like the pupil of the eye, that can expand or contract. And as it expands, it allows more light to enter and to hit the sensor. And on your camera, either from a dial or from the settings on it, you can change the setting, and these are called f-stops. And f-stops, will change. As you change the f-stop, you change the size or the diameter of this opening. For example, an f-stop that has a lower number corresponds to a broader opening of this diaphragm, allowing more light in. For example, an f2.0 will allow twice as much light as an f2.8. The next f-stop is an f4. An f2.8 allows twice as much light as an f4. And then after that, you have a 5.6, and it keeps going. It's really a logarithmic progression on this. And what is interesting to keep in mind on this is that the issues that we can talk about on f-stops are very much like the issues we can talk about as exposure time. If we're allowing too much time to light to hit the sensor, we can overexpose. Now, we can use this to our advantage. Let's say that we're out there and we want to capture an object, and there's a lot of motion, a lot of turbulence in the atmosphere, or we're concerned about star trails and all of that. We could decrease exposure time and increase the opening on the F value. In fact, if we go from, let's say, a 2.8 to 2, this has the same effect as doubling our exposure time. So we could keep exposure time the same, but just go from to a lower numbered f-stop. And so we have that trade-off, and that's often quite useful. At least it's often quite useful to me when I'm out taking images at night with my digital single-inch reflex camera. Telescopes, the f value on those is fixed. It is the focal length of the telescope divided by the aperture. And so if I have an f10 telescope, I have an f7 telescope. We would say the f7 telescope is a faster telescope because it has a bigger f value. A camera's gain. This is one that fools a lot of people. A camera's gain significantly affects the dynamic range. A lot of folks think, and I did too when I started out, and I'm still starting out. I need to keep reminding myself that. I thought, well, I want to get more light, so I just bounce up the gain. But you're going to lose something in the process. Gain is simply a signal level multiplier. That's all gain is. For example, if we have a 2x gain, what that does is that doubles the number of electrons associated with your weak signals. And so you're filling your photosite well with more electrons, but you're not getting any more information. And in the process, there's room left for electrons associated with brighter signals. And this is an illustration for that. Let's say this is what the well might look like, part of the simplicity of this, but I think maybe it communicates. With no gain. And the weak signal, the electrons associated with weak signals, let's say, brings the well up to this level. If we apply 2 gain, we're doubling the number of these electrons up to this point, and there's not a heck of a lot of room left for electrons associated with brighter signals. Now, when you look at the image, before we apply gain, those weak parts look pretty dark. After gain, they're lighter. But again, there's no more information. We're still working with the same number of photons. It's like taking this room, turning the lights down, we can't see much, shoot more electrons into the light, brings the light up, but the room is the same. We don't have any more information. We're just bringing that level up to the point where we can see it. We're just turning the lights on. Okay, noise also affects an image's quality, and this is where I have to take a slight detour and introduce a few simple statistical notions. And in doing this is going to, I hope, give us a better feel for how we understand and how we can control shot noise. Essentially, there are 3 types of variables. You have categorical variables, and these are non-numeric classifications, such as type of nebula. We can talk about dark nebula, we can talk about emission nebula, planetary nebula, reflection nebula. They're just classifications. We can talk about continuous variables, and these are variables that take on an infinite number of values, such as volume of water. That's a continuous variable. Or what a lot of people erroneously think light is like. They think, well, it just keeps coming, it's continuous, no break. Wrong. And then we have discrete variables, and these are variables that are countable. We can count them. Like the number of undergraduate astronomy majors, or undergraduate business majors, or the number of undergraduate English majors. It's countable. And this is what we will be dealing with. Now, if we take sample measurements of a variable, whatever the population is, age, income, grade point average, whatever it is, if we take sample measurements of that, we get a distribution of observations. Now, the distribution of a random distribution of measurements that produces a symmetrical bell-shaped curve is what we call the normal or Gaussian distribution. And it has two parameters, a mean and a standard deviation. And if we know the mean and the standard deviation, we know everything about that distribution. An important aspect of it, let's say that the mean of whatever this variable is 69. If we go from the mean to one standard deviation above the mean, in this case 85, we have included 34.1% of that population. No exceptions. Hard and fast. If we go one standard deviation below, we've also covered 34.1% of the population. If we look at the mean plus or minus 2 standard deviations, we've covered over 96% of that population. Now, the thing that's exciting about the normal distribution is that nearly every natural phenomenon can be described by this distribution. And even distributions that are not. We can do things to normalize them. Okay, let's keep that in mind a second. Now, the Poisson distribution that I mentioned is the distribution of discrete events occurring in a fixed interval of time. If we have a 1-inch rain, and you go out and look at your patio for a minute, and your patio is broken down into a number of 1-inch squares. Not every 1-inch square is going to get the same number of raindrops. Some are going to get more, some are going to get less. When we talk about a 1-inch rain, we're talking about the average rainfall. I may get 1 inch. Bill may not get 1 inch, even though maybe he lives across the fence. Reed, on the other hand, is going to get 1.1 inches. Okay. The Poisson distribution is appropriate when we are sampling light from deep sky object because that light arrives in discrete packets. Now, the Poisson distribution again has two parameters, a mean and a standard deviation. But what's neat about this and interesting is that the standard deviation, which is a measure of dispersion, the standard deviation is the square root of its mean. As the mean increases, the Poisson distribution approaches the shape of a normal distribution. For example, this is what a Poisson distribution looks like. If the mean is 1, this is what it looks like. The mean 2, the mean 10, and so forth. It doesn't take long before you're looking at something that looks like the normal distribution. And when we're talking about photons coming in from a deep sky object, we're talking about more than 1 or 2 photons in all cases, in most cases. And so the properties of the normal distribution can apply nicely here. Okay, now, let's talk about signal noise. Noise affects image quality. Some of that noise is controllable. And when I say controllable, I mean we can do things to perhaps minimize its impact. And examples of controllable noise would be shot noise, which again, this is random signal fluctuations around the true average photon arrival rate. So this would be like going back to that normal distribution. Let's say that the true average photon arrival rate is 1,000 photons per minute. You may capture 1,020 photons. You may capture 980 photons. Next time you may go out and capture 1,001 photons, and so on. The deviation of the signal that you captured from the long-term mean is noise. That's random variation. And we can measure that noise by the standard deviation of the Poisson distribution. Again, the standard deviation is a measure of dispersion around the central tendency. Darko-thermal current is another controllable form of noise. What happens here is that heat triggers photons. It establishes a current that will fire a photocyte, much like a photon coming in from your deep sky object. Where's this heat come from? Well, it comes from outside temperature. Or it comes from heat generated by the electronics. Now, some folks, and I think, Reed, you have a camera that cools. It's kind of like a camera that carries around its own air conditioning. And the reason for that is that the objective is to reduce the impact of thermal current. There's other ways that we can do it, and I want to comment on those. And then we have uneven illumination, such as dust on your sensor, or perhaps vignetting that you have with the camera itself. Some noise is not controllable, and this would be error that the processor has in measuring or counting photons. I suppose you could control that by going out and spending a lot more money and getting a better camera. But I think for most of us, we consider that uncontrollable. Okay, so how do we minimize shot noise? Well, again, the index for shot noise is the standard deviation of the Poisson distribution, N. A very useful, I keep hitting the wrong thing. Here we go. A useful index for this shot noise is what we call the signal to noise ratio, which is simply the shot noise, the signal divided by the noise. Okay, in this case, the signal would be the photons that we are picking up. So S refers to the photons captured, N is the standard deviation of the Poisson distribution, but the standard deviation of the Poisson distribution is the square root of the signal. So the signal to noise ratio, and this is what really helped me, is the signal divided by its square root. And we are told that if you increase the number of photons captured, you are also increasing the signal to noise ratio, which is going to give you a lot more clarity in your image. Well, it's pretty obvious why that's the case. If we increase S, the square root of S is also going to increase, but it's not going to increase near as fast. So, we can increase the signal to noise ratio in one of two ways. One is that we can have a longer exposure, or we can have a number of short exposures that are combined through an average. But what we prefer to do is to average these short exposures. And this averaging actually gives us a more accurate representation of the target than a single long exposure for a variety of reasons. One reason, as we mentioned before, a long exposure can easily saturate the well and cut off our ability to pick up signals from the brighter part of the target. Also, most noise is random. And so when we average, it gets averaged out. For example, let's say we go out and we're going to take 60 20-second exposures. And in one of these, dadgummit, we got a meteor that strikes through and an airplane that comes over. What are we going to do about that? We look at that one frame and it's ruined. We see this stuff in it. Well, when you average that in with a number of frames that don't have that noise in it, it starts to fade out, and fades out, and fades out. One of the things on this point that a lot of software will allow you to do is on your averaging to use what they call sigma clip. And what sigma clip does is that it allows you to remove, and you can set the parameters, remove outlying frames. And you can define what an outlier is. If what we see here is maybe 2 standard deviations around the mean of what we've already collected, out it goes. We're not going to include it in the average. Okay. Another thing that I think is important here, leading to the advantages of the average stacking, is as we increase the number of short exposures. So, you know, we can talk about taking 20-second exposures, or maybe we step up and do 60 20-second exposures, or heck, it's a nice night, let's stay out a little bit longer. We got our hot chocolate with us. Let's take 120-second exposures. As we do that, the average of these photon measurements comes closer and closer and closer to the true photon arrival rate. Also, in that process, shot noise as a percent of total noise continues to decrease. And to me, this is really powerful. You go out and you take one exposure, you're not going to see diddly in it. But you've captured photons. You may not see it, but they're there. One of the reasons you can't see it is you need to elevate the light level. But another reason you can't see it is that there's so darn much noise taking place that it's hard to separate what's really a true signal from the noise. And so here's the power, and I think this is probably, for me, the most important thing in the capturing process, is reducing this signal noise. And the process of doing that is so simple. Okay, well, does this really work? Well, these were some images that I've taken, and I hope you can see the difference there. This is one 20-second exposure. This is 60 20-second exposures of the Whirlpool galaxy. Now, you know, in our better projections, we could start seeing some differences. The photons that we are representing here, the number of photons are probably the same, about the same as what we see over here. But we are beginning to pick out, and it's not showing up on this, but if we look up here versus over here, we're starting to see a little more detail on the arm in this area. And if this one doesn't do it for us, an image that Dave Barrett let me borrow is this one. And of course, he really went crazy on this. These are 5-second exposures. This, the one on the left, is a 6-minute time period, averaging these 5-second exposures over 6 minutes. The other is 5 hours. But you know, you can clearly see the difference. Frankly, I think what he did is that he also did some processing on this to darken the background to help pull it out. But it's true, you know, what average stacking will allow you to do. Okay, very quickly. How do we minimize the impact of a dark current, thermal signals? Again, heat from the outside air, or the heat generated by the electronics, produces a current. This current triggers a photocyte, much as a photon would. And this is really easy to do. We control this by using what we call dark frames. And what a dark frame is simply going out and putting a lens cap over your telescope or camera. You do this at the same time, the same event that you're going to be going out imaging. I take some dark frames before I do my imaging and some after I do my imaging, in case the outside temperature has changed. It probably hasn't. And I'm probably not good enough at this. If it has, I'm going to notice the difference. And I'll take 20 or 30 frames, but I will take these frames using the exact same settings that I'm going to use when I go out to try to capture my image. The gain is the same, the exposure time is the same, everything is the same. Easiest thing in the world to do. Easiest thing in the world to do. Don't take long to do it. The biggest worry that you have is that putting the cap on and taking it off, you might jiggle the camera, the telescope a little And then what will happen is that your imaging software, whatever you're using, in all likelihood has an option where it will average these dark frames, and then it will subtract that average dark frame from your image frame, thus negating the impact of thermal current. Well, how can we take care of uneven illumination, obstructions to the obstacle path? To this, we take what are called flat frames. And this is an image with the entire field of view uniformly lit. Now, you're not going to take this the same time you're out in your imaging station. Take this in the afternoon sometime. And this is easy to do as well. You put some type of diffuser over your telescope cap or camera. I use a white t-shirt. I spread it out so there aren't any wrinkles in it. You can use some wax paper, it doesn't matter. You're just diffusing the light. And you aim it toward a bright object. I'll go outside, I'll aim it toward the bright sky, not the sun. I'll aim it toward a bright object in the light. Or sometimes, if we didn't have this on it, we could aim it toward this screen. And then it sets your exposure to automatic because you've got the bright light and things are going to go fast. And then at that point, everything else is the same setting that you're going to use when you go out in your station trying to image the Andromeda Galaxy, let's say. So gain will be the same. Your F setting will be the same. Everything is the same at that point. And again, you take 20 and 30 exposures. And your software will average these and subtract that average from your image frame to cancel out the effects of uneven illumination. Now, I have to be honest with you on this one. I don't use flat frames. I've used them, but I generally don't use them. And a lot of people don't use them. And the reason, I think, for me, is this. I don't worry about vignetting because I'm probably going to crop the picture anyway. I'm more likely to get vignetting if I'm using my Pentax camera than if I'm using something that's got a tiny little sensor like in these cameras that's the sensor's about the size of your fingernail. You're not going to get vignetting on that. I try to keep dust off. I expose the sensor and I have a little blow thing and I try to blow dust, keep it clean. But frankly, if there's dust on it, I'm probably not going to notice it. And so I generally don't do flat frames, but I do the dark frames, and I think the dark frames do make a big difference. I think they make a huge difference. Okay, so let me summarize where we are at this point. Applying too much gain reduces the image dynamic range. Image quality, the signal to noise ratio, is greatly improved by increasing total exposure time, either by one long exposure or the preferred method, a number of short exposures which are average stacked. And then you collect your dark and flat frames. Now, you've done your capturing. The images at this point are difficult to see. In fact, you may not see them. When I did the image of the North American Nebula, which frankly I think is my favorite image, I really like it. And I don't know if you noticed it when I went back there, I had the North American Nebula down here, and that nebula is all over the place, and over here, a bright star. That was Denab. I really like that. I just think that's cool. But anyway, when I did that, because of the field of view, I couldn't use one of these sensors that, the field of view is just terribly small. I had to use my digital single lens reflex camera, and I mounted it on the telescope piggyback. And I was looking at the stacked image and I couldn't see it. And I started wondering, when I piggyback, that thing's not perfectly aligned. You can't get it perfectly aligned with your telescope. You get pretty darn close. So I started wondering, did I miss it? And then I saw Denab over in the corner. I said, yeah, it's there someplace. I just need to bring it out. And so this often happens with your deep sky imaging. They appear dim, and there's a good reason for it. Deep sky objects are dim. They are dim. and they occupy a very narrow and dark portion of your dynamic range. So this is where the post-processing comes in. What you're doing is that you need to take what you have captured and elevate it to a level that you can see. You need to turn on the lights. In the post-processing, there are two post-processing tools that are particularly helpful. One is what we call histogram stretching. Often we refer to it just simply stretching. The others are what we call curves. And does it make a difference? Well, you bet it makes a difference. These are the same capture. The one on the right is mostly stretched, a little bit of curves. I don't use much curves. I kind of go with what I got. But I think, stretching makes a big difference. And so, how do we do stretching? Well, this is an image histogram. It's the image histogram of this image. This is not mine. I borrowed this from Charles Bracken. I thought he laid it out nicely, and he graciously said I could use it. I got to stop playing with that. There we go. The horizontal axis represents different degrees of brightness. On the left, the darkest dark. On the right, the brightest white. The vertical axis represents the frequency with which that brightness level appears in the image. So we can see from this, we can't see a darn thing. Incidentally, this is NGC 281 up in Cassiopeia. All of the light from that nebula is captured in this spike. Now, if we could take that spike and stretch it out across a wider range of brightness, we can reveal the information captured in that spike. And that's what you mean by stretching. Now, the dynamic range is fixed. So how do we make room for the stretching? Well, we make room for the stretching by getting rid of portions of the histogram where there's no information. And we do that by clipping down here and clipping up here. And in your software, there's usually, a caret or something you can move back and forth to indicate where you clip. This is referred to as setting your black level and your white level. This is what we have after stretching. And this is what the histogram looks like after it's stretched.
Huge improvement.
Yes.
Fantastic improvement.
Yeah, you can see the darn thing. And I got to tell you, when I did the North American Nebula, I really got excited. When, I was looking at that image, I didn't see anything but black and denad. And I started to stretch that sucker, and I started seeing red appear. And I thought, I got it. And I stretched a little bit more, played with a little bit more, and by golly, it was there. That was exciting. Okay. I do my stretching. The previous one, I think he stretched with probably Photoshop. I don't use that. I use GIMP, which is a great software like Photoshop. It's free, which appeals to me. No subscription on or anything. It's time tested. GIMP is, and this thing is being upgraded about every 2 or 3 months. GIMP is written by a bunch of people that are software developers. Some of them may actually do the developing on Photoshop. And what they did is they put this together as kind of an experimental platform, and it became very popular. It's probably not as good as Photoshop if you're a professional photographer and you do landscape stuff or portraits. But in terms of what I'm interested in, which is mainly stretching and curves, it's just as good. And this is what it looks like. This is the Whirlpool Galaxy after I stretched, and up here you can't see it, but there's some carats that I can slide back and forth to do the clipping. And I want to do a real quick demonstration of that in a moment. Now, after stretching, we may wish to enhance the contrast or to reveal a fainter structure. And this is where curves come in. Curves allow us, they take brightness levels in the current image and allow us to increase that brightness or decrease that brightness in a follow-up image. Okay, this is GIMP again. Let's look at this. Okay, the horizontal axis, complete dark to the brightest white, complete dark to the brightest white. The horizontal axis represents the current image. The vertical axis could represent what we might see in a follow-up image. And here we start with a 45-degree line, and if the 45-degree line isn't there, you imagine it. Now, why 45-degree line? Pick any brightness level you want down here. Come up to the 45-degree line, go across, it's the same level of brightness. So with a 45-degree reference line, we're saying that the brightness levels we see in the current image will be exactly the same in the follow-up image. Now, your software will allow you to grab a hold of this line and to pull it up or pull it down. That's what we call by curves. Why would you want to do that? Well, here we pulled it up. Again, imagine the 45-degree line. When this curve is above the line, every current level of brightness will appear brighter in the follow-up image. Doesn't matter where we start. Start here, current level of brightness, go up to the line across, brightness level in the follow-up. And you can see what it did to the dumbbell nebula. Now, conversely, again, imagine the 45-degree line. If we pull that curve down below it, that says that current levels of brightness will be darker in the follow-up. Take this level of brightness, what it'll be in the next one. And so, this reference can be very useful. Now, sometimes you might say, well, I want to enhance contrast. There are certain portions of this nebula, let's say, that I would like to darken and certain portions that I would like to elevate the light on. And so you might look at an S-shaped curve. So what we have here, again, we can see the 45-degree line. Brightness levels here will be darker in the follow-up image. Brightness levels here will be brighter in the follow-up image. And you can play with this all around. I really want to show you, what I did with curves on the image that I took of the sun. Because, there you have so many different levels of brightness going on that you play with this all over the place. And again, you look for what seems to be rather pleasing. Okay, just finish up this portion of things before I get into some perhaps application. Popular and free software. Capture software. I use SharpCap. A lot of people use SharpCap. And it will capture videos, and this is what you use if you're going after planets or the sun or the moon. So you can set it, and maybe you're going to capture, have a video of 3,000 frames. It'll take less than a minute to capture it. And each of those individual frames is what ultimately will get stacked. If you're going after deep sky targets, you're not going to use fast videos. You're going to use long time exposure. So you can set it to, okay, I want to take 60 images, 20 seconds each. And then, and this is, a deviation from my statement of free, it has the capability of doing a live stacking. I think this is the coolest thing in the world. It is fun. When you download, the free download on SharpCap, live stacking is there. You just pay them $18, and for the next year they give you a key, and you can use it. It just basically unlocks. But and $18, frankly, I'll spend more than that at the baseball game getting hot beer and a cold hot dog. this to me is this is one of the best $18 I spend every year because it does it all. And what's great about it, you sit there, you're out there and you got your screen in front of you and you can watch it happen. You got this frame and then it brings in the next frame and it averages as many.
It's somewhat like the old photographic process where you were watching the picture come up in the developer.
That's what we have happening here. And in the process, if you wanted to stretch as you went along, you could do it. If you want to do color balancing as you go along, you can do it. If you want to do curves as you go along, you can do it. You can do it all from that. And then Auto Stacker, you can take the images that you captured here, drag them into Auto Stacker, and it will do the average stack. I mean, it does other things, but it'll do your average stacking. And then if it's a planet or something like that, you want to bring out more detail, you take the stacked image and you drag it into Registrack, which does wavelet processing, which really brings out the detail. And I have to comment about wavelet processing in a moment. Most folks will say on wavelet processing, they'll say, guys, it works. Don't ask how it works. Just accept it as a free gift. Well, I wasn't satisfied with that, so I kind of have a notion of what's going on. And with that notion, I don't know if I'm right or wrong, but it sure helped me. I think I'm right. Okay. Here are some images from SharpCap. This is an image of Jupiter, and I took this about a month ago. An image of Jupiter unstacked. I drug the video file of this into Auto Stacker and I stacked. And this is the stacked image of Jupiter. And you can see the difference in the noise. It really smoothed that noise out. But there's a lot of detail here that isn't brought out. So I drug this over to Registack and did wavelet processing, and I started to get details on the bands. These bottom images, this one of the Dumbbell Nebula and this one of the Ring Nebula, I did that from start to scratch using live stacking on SharpCap. Again, it captured, it averaged stack, it stretched, it curved, color balanced, did it all. And when I got through with that, I said, I like that. I'm stopping. I'm not doing anything else to it. I'm just leaving it the way it is. And for $18 a year, boy, I tell you, I love it. And then a few other software that is free that I use. IMPPG, I use this. This program was written specifically for processing solar images. And you do your stacking of the sun with this. And there's a few tricks in there that are really neat. And I've already mentioned GIMP. Astronomy tools, I suspect you may use this. The thing I like about astronomy tools, and I always refer to it before I go out and do any imaging. You can put in there, what telescope you're using. I mean, it has a list of a bazillion telescopes. You're going to find yours in there. You can put in what camera you're using. And it has less than a bazillion, but you're probably going to find your camera in there. And then you tell it whether or not you're going to be looking at this and what your target is. You can put in the Messier number, you can put in the NGC number, and then it will show you this item, let's say this galaxy, and draw a square around it so you know what your field of view is like. And so, you have one field of view if you're just imaging, another field of view if you're viewing. And on that, it gives me an idea of, do I want to use the big, the Me telescope? Do I want to use the Astrotech telescope? Do I need to be using my digital, my single lens reflex camera on this? Because of the field of view, that really helps. I really like that. And then this last app is just a little thing on the phone that does a better job of telling us about imaging conditions, whether or not we are imaging things like planets or deep sky objects. And it really does a good job. A couple of weeks ago, I wanted to go out and image Jupiter, and it looked very clear. I mean, it just looked like a beautiful night. I said, man, this is the night for it. And I looked at this app, and it had a big gray circle, and which says, hey, this is not the best night for imaging planets. And I thought, well, I don't really believe that. I went out, and it turned out there's a lot of turbulence in the upper atmosphere. And when I got Jupiter and I was seeing it on my screen, this thing was bouncing around like a yo-yo, and there was so much turbulence in the air that the colors kept changing on it. And I thought, yeah, well, you know, there's something to this. So I like to refer to that as well. Okay, well, that's kind of it on that, and I want to take, if I can,
Sure.
just a few minutes to demonstrate some of this software. And because I think some of this stuff's pretty cool. And this stuff goes fast, so I'm not going to be holding you up here for too long. Okay.
So
I was gonna
Parker, on the dark frames, so if you've got a camera that's got like a hot pixel or something like that, is the dark frames what'll take that out?
Yeah, it'll see it, and it will subtract the average dark frame from your image frame. So it ought to cancel that out. Okay, let me come up here to SharpCap. I was going to plug my camera in to show you on that, but I'm not going to. Let's just give you an idea of what we have.
Dark and flat frames both have an impact on that.
What you do on this is that you tell it what camera you have, and if I had one of my ZWOs in here, it would be listed, and I click on that. Let me just kind of go down here to test camera, deep sky. So, you know, it would show you the deep sky object, and then the thing over here is that I can do my color balancing, line up my red, green, and blue histograms. If I want to take some dark frames, I come over here to capture. I come down and I click on capture dark, and then, and I tell it, you know, I want to capture dark, and then it says how many you want to capture. I want to capture 20. And then I start. And then when that's done, I can come down over here and I can tell it to subtract dark, and I can browse and I can click on the folder that has the average dark in. And if I don't remember what the average dark was, there's the last folder that it puts in there. I mean, it's that simple. It's that simple. And then I come up here, you know, to do my live stacking. And on the capture, I tell it how many images I want it and what the exposure time is going to be. I can come over here and I can adjust the gain, adjust the exposure time. I mean, it's that simple. It's that simple. And you don't have to sit down and restudy software manual every time you do it. It's pretty obvious when you do this. All right, let me come over here and show what we can do with the stacking and the like. This is an image of Jupiter that I captured the other night with SharpCap, and this is the video. You can see it bouncing around some. Okay, what I'd like to do is that I want to stack that video, so I'm going to use AstroStacker to do that. AstroStacker's got two windows, and I just drag up in the viewing window. Close that out. And let's get this image. up here. You know, I can play that video. You see it bouncing. You know, here we got a couple of the moons, and down here we have another moon. Over here I have my controls. And what I am going to do, let me clear that, I am going to decrease the size of this picture. Decreases really a lot, because if I was doing my stacking, it's going to do some analysis of the quality of the image. And I don't want to spend a lot of time, a lot of memory, a lot of buffering, analyzing what's dark. And so I just adjust the size of the picture, so I'm essentially covering the size of the planet. And then you will put in little boxes where it's going to analyze the picture. And I'm going to put in some tiny little boxes of analysis. So I'm going to do that around where I can see some details. So can you see this is going up around the bands? And you know, there's some stuff going on up here. You don't want to put these where they are, you know, getting in the background much. And then I kind of like to cover the whole thing, so I'm going to increase the size. So I'm going to put in maybe 4 or 5 of this. And what I've done is that I have, at this point, defined areas where it's going to analyze the stability of the individual frames. So this is a planet. And let me just kind of go down and let's just analyze the quality of those frames. Doesn't take long. Over here, the reference is the best quality image, and here's the weakest quality of my images. And I'd say I have a lot of images that, you know, we're pretty good. They're above average. So what I'm going to do now is I'm going to tell it, now I'm going to, if I can see this, what percent of my images I want stacked. Oh, incidentally, I checked this reference frame. I said auto size. What this is going to do is that it's going to stack some of the best frames I have and then use that as a reference for stacking the rest of it. What the heck, let's stack half of them, probably more than we should. And so over here I'm going to put in 50, it's going to stack 50%. RGB align, so after it stacks I want it to align my colors. Drizzle, what drizzle will do is that if you have a poor quality image, it will fill in for some of the mixing pixels. I don't want to do that. So let's just go ahead and stack. Stack, didn't take long. Okay, well let's see what we got when we go to my folder. Okay, this is what we had. It looks a little bit better than what we had before. But now what I want to do, and this is where most folks say this is magic, I want to bring out some detail. And I'm going to do that by dragging this image over. Okay, let me just get that little folder screen. We're going to do what they call wavelet processing. And a lot of this is mystery. In fact, most of the sources will say, don't try to understand, just do it and play around with it, experiment with it and see what works. Well, I'm not one to feel comfortable with that. So what are wavelets? When we look at an image, if not much is going on, we get a fairly smooth, almost like sine wave type of image coming in. Now, if we are hitting areas of contrast, that's where we get into what is called wavelets, and suddenly that nice smooth sine wave goes crazy with varying degrees of wavelength and various degrees of amplitude. So we got a smooth part of the planet. We get to some interesting detail, and then we get smooth again. Now, if we take this stuff going on and we compress it, what we're doing is that we are sharpening that image. You know, a parallel might be music. If you take a sound wave and you compress it, you're going to pitch it up a higher octave. That's sharpening. If we take this thing and we stretch it out, we are lengthening the wavelength and we are reducing the amplitude. In music, that would be lowering the octave. That smooths it out. Now, what this software will do is that it has 6 different wavelet areas. And basically, you start at one and it's going to be focusing on the finest detail of the image. All the way to the 6th level, and it's dealing with broad areas. And so it's almost like saying, you know, look, let's look at the tightest detail that we have in the image, next tightest, etc. And you can do wavelet adjustments independently on this. And let's just start down here for the fun of it. I'm going to increase, you know, maybe the intensity level of it. And then we have a little slider that indicates the percent of what I just did that's going to be applied. And notice what's happening. I'm bringing out some pretty nice detail there. Now, as we bring out that detail, we're also introducing noise. So I can come over here and I can say, all right, let's calm this noise down. So I have a denoiser, and I'm just going to boost that up a little bit. And then let me go to the next level of detail, which is not quite as fine a detail on the planet, but still pretty tight detail. Now, just for the illustration, let's just really jack this up. Can you see the difference? And this is where, you know, processing, I said, you know, a lot of it's kind of, you know, personal taste. And I was, you know, what do you want to see on this? You know, what's pleasing to you? And what might be pleasing to me may not be pleasing to you. So this is what we are doing with wavelet processing. Okay, I'm going to do 2 more. I'm going to illustrate stretching, and then I want to go to that image of the sun, which I think is kind of nice. Okay, 20-second exposures. I took 60 of these things. And this is, again, I want to bring out the details, so I'm going to do some stretching. You can see where the histogram is. And there's a lot of stuff here that's wasted information, down here and up over here. I'm just going to drag this over. What I'm doing is I'm cutting off this portion of the histogram where there's no detail, no information. And I can see more. Let's cut it down over here. See what's happening? I'm bringing out that light. And again, it's a matter of taste. Where do you want to shut it off? And we could do, you know, curves in a similar way. I'm not going to do that. Let me just jump right now to the sun and do some, well, I think some fun stretching on that. And then I'm through. What's going on here? Look at this stack sun, I am PPG. I'm thinking I'm going to do sun, I may be wrong. Did not open. Why can't we open? show it to you. But what I did on the sun, on the curves, I had the image of the sun, and I wanted to try that one more time. Well, okay, let's try that. I wanted to bring out, some contrasting detail on the sun, so I wanted to apply some curves. And I played around with it, and, I was getting both prominence and the surface granulation that was fairly pleasing. That's kind of what I ended up with. But it was taking me a while to get there, and one person suggested, well, why don't you inverse the darkness on the image, so the black became white, white became black. They said, kind of then work it from the reverse. And I did that, and boy, things just popped out immediately. And they said that almost all the images that we see from the sun, they do it that way. It just seems to fall in place a lot easier. I was really pleased with this. This is actually the first image I took of the sun. Got some nice prominence there. I like these filaments, which are, the prominence, that same thing as these. It's just, on the surface where, it's coming at us rather than on the edge. And picked up some sunspots. Detail on this projection is not terribly great, but, we can see a lot of what have to be folds from magnetic lines and the like. But that's where I am, and so the next thing I'm going to do is, like I said, with the exception of this, everything I've done with the color camera. And now that I have the monocolor camera that I know is going to give me 3 times the pixels, and in fact, I want to go out and experiment with that. In fact, I think the first thing I will do is that I will go out and take some galaxy images, with the monocolor, and then on exactly the same settings, do it with the color camera, and I want to compare the details on those. And if I have anything interesting over several of those, maybe some night I can steal maybe 10 minutes to just quickly flash up the comparisons.
So let me ask you a question. Let's say the mono camera does give you substantially more detail. Can you use the mono camera with red, green, and blue filters to make
yes, you can.
Colored image that will have more detail?
Yes, yeah, you can do that. You can put it on a wheel. I anticipate that rather than cutting in third the exposure time that I would have on each, what would be the normal image in session, let's say half an hour, now becomes an hour and a half. Do the half hour on the red, half hour on the green, half hour on the blue. But no, I think that's what I want to do, and I'm anxious to talk to Dave. If you haven't looked at his planetary image, and Reed's got some fantastic images. If you haven't looked at theirs, you really ought to. My guess is, are you using monocolor or color?
Mono.
Okay, and my guess is that the difference, when I look at the quality of what you guys are doing and this, is that there's 2 things going on. One is you're using the mono, the other is you're just a hell of a lot better at than I am at this point. But I'm anxious to give that a try, just to do a comparison and see what they look like.
I think you're like my techniques on the processing need a lot of improvement, but I think that you're going to find when you use the mono, if you can use a hydrogen filter, and just that helped a lot. If you can devote some time just to collecting the hydrogen emissions for some of the deep sky objects, because that filters out so much noise and so much, you get really good contrasting.
Well, and thanks for that suggestion. and I will do that. And that makes sense because a lot of what we're looking at, deals with, the hydrogen and the oxygen.
Yeah, it's like an incredible, it's like the best filter, because nothing else gets through.
Well,
And,
I have to confess that I have a hydrogen filter. When I get out there and I finally get set up, I am so anxious to get going that I haven't bothered to play with the filters, but I need to, and I appreciate that suggestion. I will do that.
yeah, with the mono, and then you can just add that to your red, green, blue,
Okay.
and then hydrogen out, hydrogen.
Do you use a wheel?
Yeah.
Okay. Yeah, I think that's my next
Yeah,
step.
it'll definitely boosted my, the contrast and everything.
Well, you are definitely going to get a call from me saying,
Yeah,
put on your winter coat and stocking cap.
yeah. But these are just wonderful. These are wonderful. Yeah. Such a nice job of
Mhm.
Well, that's it.
I got a question about your experience with that lunch scope.
Yeah.
I have the same scope, I think. I have the version 1. I don't know if you've got the version 1 or version 2.
Well, whatever they were selling this summer.
Oh, you got the more recent one.
Yeah.
On mine, when I dial that to fine tune the filter, I don't get the same result across the whole sun at the same time. It sweeps across it, so I might get prominences on one edge, but down in another spot I've got surface detail. From the look on your face, I'm guessing yours does not do that.
If it does, I haven't noticed that. When I dial that in, I will home in on a section of the rim where there's a prominence, and I do my adjusting. I adjust the focus first.
Yeah.
And then I start playing with that pressure tuner. And I just play with that until, okay, I got the prominence. And now what I need to do is to work on the granulation. Because I think I'm going to see more detail. I want to see more detail in the granulation if I got the prominence. I haven't noticed the other, but quite frankly, I haven't looked at it because I've been really focusing on a section of the rim.
Right, so maybe if you pull back so you're seeing the whole sun, you'll get prominences on one side, and then as you dial it, they'll fade away and prominences will pop out on the other side.
That's interesting.
That's what I get. I don't know
Yeah.
what yours will do.
That's a good little scope.
I've enjoyed it.
Yeah, that's a good little scope. I'm really impressed with it.
All right.
Okay.
Well, thank you.
You bet.
Yeah, that's great.
That's my 15-minute presentation.
You picked a good night for a 15-minute presentation.
Well, I figured that you wouldn't be going out and setting up the
Yeah.
telescope. So.
I had another question. On one of your scopes, I noticed you had a star diagonal ahead of the camera.
Yeah,
What's that for?
keep me from bending down.